Welcome to the Brown Bag on corrosion engineering and specifically our studies of our flexible channels and some bonus projects at the end. I'm here with two co-presenters. We have two fellows from Pivot Engineering, Michael Ahern, who's a partner with the firm, and Pivot Engineering specializes in corrosion and structural engineering as well. They're both out of Austin, Texas. Michael's went to the University of Texas, MS in structural engineering. He's a Longhorn. We have Randall Poston, also a partner with Pivot Engineering, and also University of Texas, Longhorn. And Randall most recently has been recognized by Engineering News Record as the top 25 newsmaker in the country for this last year for his work as chair of the American Concrete Institute Committee on the Concrete Code. Reorganized the whole concrete code, which was a big effort. And, so we're really happy to have him with us here. Now, Randall was in charge of the study originally, and he was previously with WDP, the firm that did the work on this channel corrosion study with the county. Randall and everybody else in his Austin office has now formed Pivot Engineering.
Yes,
So they're a new firm. And so let's get started. So just to give you an outline of what we're going to talk about, initially, what caused the whole emphasis to do a channel corrosion study. Failure at the Oxnard West, not Oxnard West, the Oxnard West train where we have a wall failure. We'll talk about that a little bit more. We're going to talk about the basics of corrosion, the investigative methods we used, channel investigation results, and then we're going to talk about some other cases. So we have a lot to go through. But we'll do as fast as we can. We actually could probably have a 3-hour session on all this, but we're going to squeeze it into 45 minutes and questions and answers. So let's start all this. Back in December 2013, we got a phone call from the city of Port Hueneme that part of Oxnard West had collapsed. So you can see this wall section right here had completely collapsed into the channel. This is on Channel Islands Boulevard. It runs parallel to the channel inside. The channel's inside the road actually. And we were fortunate that the wall section was actually on the inside of the channel, not along the roadside, because that could have caused more failure situation. If vehicles had come along, it could have actually been the channel. So it cost about $500,000 to fix this in emergency repair. DOC did the job, but we obviously don't want to be repairing 20 feet of channel, 40 feet of channel for $500,000, every month or two. So we got to figure out what's causing these problems and try to head them off so we can get them fixed. So, what other symptoms are we seeing in our channels? Well, we've got gabber, wall deflection. We put up stress to support the wall. You can see the deflection here. Dry canning, same situation. We're seeing deflections in the walls. Other symptoms and problems are rust patterns that you're seeing within the walls themselves. You're seeing spalling. So we decided we were going to do a study. We hired WDP to assist with us. And we really set up two goals. What are the condition of rebar in our high-risk channels? We'll talk about what a high-risk channel is in a minute. So we picked 5 channels: Oxnard West, Oxnard Industrial Drain, North Simi Drain, Dry Canyon, and Gabber, to look at specifically, because we considered those high risk. And our second goal was to determine whether we could find non-destructive methods to predict actual corrosion in the walls, and then confirm that with destructive tests. So that's real key. We don't want to go around having to dig holes in all of our walls to see if there's corrosion. We may have to do that at some point, but we want to find non-destructive methods that we can use, instrumentation that we can use to test these walls and predict the corrosion without having to dig into them. So here's typical wall sections from the 5 channels we selected. And this will help us indicate what's considered a high-risk channel. We've got our oldest Gabber channel, dry canyon lateral, vertical wall construction, single matted steel. They're only about 6-7 inches line at the top, and again, one mat of steel holding up the whole wall. And in some cases there's a starter wall, in some cases there's not. The wall is built directly on top of the imprint slab. When it's on top of the imprint slab, that may allow water to easily get in through through the cold joint and access the steel over a long period of time. A little more sophisticated design, North CV drain. Still one mat of steel at the top, two at the bottom. A little thicker sections. Oxnard West, Oxnard Industrial drain. More sophisticated designs, two mats of steel. Now, what's important about that is the rear steel is actually the steel that's holding up the wall. So corrosion of this steel, if this was to lose its strength, then what's holding the wall, what's preventing the wall from collapsing, it's really just the weight of the wall, friction at the joint. There's not much holding it up. When you start to see deflection at the top, then you know the steel is most likely losing its strength. Other factors that we may consider something a high risk: access to salt water, chlorides, high groundwater table. As we'll talk about the reason what causes corrosion, you'll see why those become high risk factors. Okay, corrosion basics.
Thank you, Carl. So, don't want to get into a whole lot on the kind of corrosion mechanics, but basically it's a lot like a battery in your car. And you know, steel, when it's manufactured, just the nature of steel, it wants to go back to its natural state, which is iron. So as soon as you take steel out, reinforcing steel or any kind of structural steel, it immediately starts to corrode. It may be at a very, very slow rate, but nonetheless it wants to corrode. Concrete provides a very high pH environment, so as long as you had a high pH environment for the concrete, it passivates the steel and it's normally very well protected. But what can prevent or depacify that steel whenever you get cracking, wherever you get penetration of chlorides, whether it's through a crack or water in their oxygen, or just over time as they begin to seep in through the concrete, you can eventually depassivate and form a corrosion cell. And there's different types of corrosion we call macrocell corrosion, microcell, and one of the forms that we've had here is microcell, and it's very, very tough to detect, and we'll explain that. But normally concrete very, very well, protects steel very, very well, and so structures, reinforced concrete structures can last a very long time. Your particular flood control channels are unique because you have, up river, so to speak, kind of natural water closer to the channel. The salt water in the tidal zone can be exacerbate the effect of creating a corrosion problem. So there's no single device. I wish I could take this device and go up there and from a distance and say you got corrosion, and there's no such device that we have. But we have a lot of tools in the tool shed, so to speak, that we can use. Certainly visually you want to go out and look if it's deflecting. That's certainly a big sign, but that's probably too late. We do invasive probes. Radar is able to help us detect where reinforcing steel is, where we might want to probe. There's chemical tests that you can do for what's called carbonation, which can be a driver of corrosion. We can measure the amount of chloride that's in concrete. There's the nature of corrosion. It's an electrochemical process, so there's a test you can see if it's continuous or not. The methods that we typically use, the half-cell potential method, which was actually developed in California by a highway engineer named Robert Stratfel back in 1974, and a lot of bridge decks and Caltrans, they went out and developed a method. It's a fairly simple method, but you're able to detect the presence of corrosion, but you can't tell anything about the rate of corrosion. So it helps, but it doesn't tell the whole story. There's also this method which we have utilized for over 20 years, Impact Echo. It's a non-destructive method for assessing the integrity of concrete, and we'll show how we use that specifically for corrosion. Also, we can measure in situ concrete resistivity. Since corrosion is an electrochemical process, the more wet the concrete is, the more conductive it is, the higher the potential for corrosion. So again, it's another test, but it doesn't tell the whole story. And then finally, destructively, we can take the concrete out, take a look at it, see what the permeability looks like, what the cross section looks like, and under a microscope, and that's known as petrographic analysis. So, probes, we went in and some of these high-risk walls, we looked at areas where we potentially thought would be a problem. Here along this joint at the gather channel, you could just kind of tell the nature of the concrete between the bottom slab and the wall section itself. Is vulnerable. It's like a construction joint. It's not, the concrete wasn't necessarily well consolidated there, so you can imagine water being able to penetrate through that area. And other areas of construction joint with these starter walls might be a little higher. So anyway, we would do probes. So the steel of interest, though, is really not the side that we're looking on necessarily on the channel. Some of that was single reinforcement towards the backside, so we actually go to the trouble of looking at on that backside where the reinforcing steel is the closest to the water and moisture ingress. But you can see here we've got different conditions. You can see the bar looks fairly clean here, but you can see some corrosion product here. Same here, these bars look fairly clean, like there's not much corrosion activity. And this is the type of corrosion that makes it more difficult. It's both macrocell and microcell. You can have very, very small areas that are corroding very, very fast, but they're very, very difficult to detect. So radar, all radar does is give you an idea of where reinforcing steel is, so we know to go out there when we do our probes, and it doesn't take much figuring, but with the radar signal, you can see where we have these little hyperbolic signals, and it gives you an image. That's really the reinforcing steel. So we know to go in there how to capture the area of interest when we're taking a look at it. Carbonation methods, a chemical test, wherever it's red is high pH. We don't have to worry about it. There's a natural process that occurs that this layer up at the top can, where the pH gets lower, where corrosion can be vulnerable in highly industrial areas of the United States. This corrosion or carbonation front can move down. When it's at the level of reinforcement, say down here, you can get carbonation due to corrosion. That's not much of the occurrence that we see here in the Ventura County walls. Chloride contamination. Chloride, in essence, can be thought of accelerating the corrosion whenever we get more than about 300 parts per million, which is the threshold that we're concerned that we can get chloride-induced corrosion. We had some cases of that. And then this half-cell potential test, again, a method where it tells us whether it's corroding or not corroding, but based on these threshold values, but we don't really know how fast it's going to corrode. And that's really what you want to know. How fast, if we know that steel wants to corrode, go back to its natural state, but is it going to take 1,000 years or is it going to take 5 years? And so that has to do with the rate of corrosion. The impact echo method we use, it doesn't detect corrosion. What we're doing, it's like ultrasonics for steel. We impact the surface of the concrete and it sends out what we call a stress wave or literally a sound wave through the concrete. And wherever there's a defect, we get a reflection off that. And the reflection is fairly easy to see. You can see this kind of signature here where it's a very sharp peak. That tells us it's solid through this. But here we get a shift and we get some other higher frequency peaks. That tells us the concrete's not solid. So what we're doing is going near that starter wall joint. And if we do the signal there, if that joint is very good and it's acting as a composite, well consolidated concrete, we won't see a reflection. If we do it there and we get this type of signature that tells us it's not well consolidated, that means it might be vulnerable for this water to come in at that joint. So that makes it a higher risk in terms of your particular channel walls. This is the corrosion rate half-cell test. We have to connect to the reinforcing steel, so we have to find the reinforcing steel at some location with the radar. We connect in. This is what's called a half cell. It's actually copper sulfate. And by taking a voltage reading these readings tell us whether there's active corrosion. And that's the corrosion rate, or the corrosion half-cell test. Now, there's also a test where we use a corrosion rate device, and it will tell us what the actual rate of corrosion is. And in that case, the device gives us some indication of what life expectancy we have in the steel. It's the test is good, but it's not. It can be misleading at times. So we have to do some interpretation of it. The other thing we can do is use this little concrete resistivity device. We can put it on the concrete. It really tells us how conductive the concrete is. If it's very wet, drives down the resistance, it means it's very conductive for electron flow, for corrosion. If it's very dry, that would be the case where you're getting the resistivity is kiloohms per centimeter. You can see we get numbers that are like around 200. That means the it's a very, very negligible permeability. So it gives us, again, it's another indicator. It doesn't give us an absolute in terms of the amount of corrosion that occurs. So this was some of what we see. This Oxnard channel wall, the failed panel. You can see at the base here. You kind of get a feeling that this concrete, when it was cast on I can't remember if this was a starter wall or a base slab. I believe it may have been a starter wall. And so you can see there's a lot of roughness there. It allowed a lot of penetration of water and oxygen over the years. You got a lot of corrosion products at this location. But it's very localized. I mean, it's right along that joint. You get 6 inches away from that, it's perfectly, pretty much perfectly clean reinforcement. Very well protected. So the challenge is really, can we detect this sort of thing without having to go in and look everywhere? And we'll talk a little bit about what we found from some of the results. This is so we take a wall panel here. This is one of the panels, Oxnard West channel. These are the half-cell potentials, and we're going along for this station 50, our panel 57S. You go from one side to the other side. Wherever it's red is an indication where the corrosion half-cell potential, when it's more negative than -350, it tells us there's 90% chance there's active corrosion. When it's between about 100 and 350, there's not much chance, and where it's more positive than 100, there's no activity at all. And so you can see we've got a zone here near the very bottom here that's the hot spot, where that joint is. Everything else it's inert. We haven't had much moisture penetration. It's been pretty inert over all these years. We also did some corrosion rate test. The highest value we had is 0.13 in terms of corrosion rate. That's a fairly low corrosion rate. So even though we had active corrosion, the rate of it wasn't necessarily overly aggressive. So we were able to detect the corrosion, but the rate wasn't well. So then when we look at it, there's a few hot spots in this area, but not a whole lot. North semi-drain, same sort of data, except in this case you can see the wall is pretty active everywhere in terms of the potential for corrosion. All red, and so and then when we look at the corrosion rates, when we look at very low, this 0.44 value, even though it's low, it's at the higher end of low, and again, you can see corrosion products coming out of this joint. It's clearly active corrosion, and went in and we can detect that this was from this impact echo test, and you can see we don't have that one clean spike. We're getting multiple reflections. That tells us that concrete surface between the wall and the stub wall isn't very good, so it's going to be at higher risk to corrosion. So, you build a picture. You do these various tests. You can kind of build a picture of what seems to be more vulnerable to all this. This is the problematic here, right? So we have this bar, and you have this all of the steel from that probe, 100% corrosion at that joint. And you look at this rebar here, you look at this rest of this rebar here, you look at it here, and there's hardly anything occurring. So when we get these microcells, and these microcells are formed we get a very hot, low oxygen with a high amount of water there. It forms a cell such that, and it's very aggressive, we call it an autocatalytic process, so it's very, very advanced. This type of corrosion that we have here is virtually impossible to detect with the type of technology that we have right now. And this is the most pernicious. I mean, it's really taking all the area of steel, and when that happened, it did in Oxnard West, along the whole joint, those walls have no redundancy, they're going to collapse. We also found some other things petrographically. There was some ASR that was detected in there, but that forms an internal cracking mechanism. There's this area in California, there's a lot of incidents of, can be a lot of incidents of ASR because of reactive aggregates. So that just adds to the process of where you might get some more permeability or cracking, allowing access to both water and oxygen. Gabbert channel, which was built along, you can see here, we got a corrosion product, very localized. The most exposed bars showed very severe corrosion very locally, but you get away from that, it's very difficult to detect. This had a fair bit of chlorides. That chloride testing, there was over 300 parts per million, which is the threshold value. So this is chloride-induced corrosion, which even further accelerates the corrosion process. The cover, just from our radar, was in front of the wall, had pretty low cover, did not have what was prescribed in the original drawings. So all this, concrete quality, the amount of cover, the consolidation of the concrete at the wall joint intersection, the access to chlorides, all that builds a picture of what makes this, a difficult problem from a corrosion perspective. So overall, in these channels that we looked at, there's little corrosion damage that was found in the industrial drain section. Oxnard West had, high potential for damage. All these corrosion rates, the chloride tests, and resistivity tests that we measured say it's at high risk, but we didn't really find much. So it's not a great conclusion in terms of that. We know it's at risk, but we didn't find a lot of corrosion manifesting itself in those particular areas. North Semi Drain, we found both the extensive high potentials and damage and some ASR. So this one was ripe for corrosion. Dry Canyon Drain, high potential corrosion potentials and damage. Gabbert Channel, high corrosion potentials and damage. So the only one that's a little bit misleading here from our non-destructive test was really the Oxnard West Drain, which is where the panel fell. We had high potentials. All the indicators were there for a lot of damage, but did not really find a lot of additional corrosion damage in those particular areas. So, these channel walls have performed well. They've had a good service life. Of course, we want to extend the service life. We've got, like another 40 or 60 years. We had the similar challenges. We worked on the Marina del Rey seawall, which is the area north of LAX, and they had similar problems with wall panel failures, and they were not adequately designed for the seismic event, so they had to go through a retrofit of the entire 7.5 miles of seawall. And you can imagine that that's fairly expensive. You have, how many hundreds of miles of channel? I can't even, 216 miles. So it's a big challenge, a lot of infrastructure. This is what we're dealing with across the whole country. We've got aging infrastructure and, little, as small resources as we have, but you got to do something in order to try to extend the life. So in summary, we kind of look at the study goal 2 from the aspect about, what can we use from NDT. Visually, of course, when you get to cracking and movement, it's already getting too late. It's holding on by a thread at that point. But certainly we can use visual indications if you do that on a routine basis. It certainly is helpful from an agency point of view doing routine visual inspection. The surface penetrating radar you can't use, it's only good for looking at locating the rebar, but then it gives us an avenue for going in and inspecting it. Carbonation, we really saw no carbonation out here. It's not like these industrialized areas where you get this carbonation, so don't have much concern for that. Chloride contamination on itself, we found isn't an indicator. You can have high levels of chloride, but if it's good concrete, not low oxygen, low water, you won't get much corrosion. So in and of itself, it's not a test that's going to tell you anything. Same with the continuity. Half cell potential was one of the better indicators that we used. Yes or no. We got a little bit of a mixed bag at the Oxnard West, saying we had high potentials, but we did not see a lot of corrosion. Impact echo, we felt like was a pretty good indicator wherever we were able to do that test next to the joint. Got a shift in those frequencies. It told us the concrete consolidation wasn't good. The voiding, there was access to moisture and oxygen, was a pretty good indicator of corrosion. Corrosion rate was much like the half cell potential. It gave us some information. It was kind of a mixed bag of whether it told us something or not. Concrete resistivity was one of the easier tests. It was a pretty good indicator when we did that surface test of was there a lot of moisture in the wall, and therefore did it coincide with the corrosion rate? Destructively, of course, if we could go in and put a probe at every bar for 200 and something miles, it'd be great, but it'd be a lot of damage to the concrete after we got done. Petrographic analysis gave us, we wanted to make sure there weren't other outlying mechanisms like ASR. We did find some trace elements of ASR, alkali silica reactivity in this concrete, but it wasn't so extreme that in these channel walls that we were necessarily concerned about it from a moving forward perspective. So that's what we wanted to present relative to our kind of investigation, and Mike is going to, we're structural engineers at heart, but I've been involved most of my career a lot in corrosion, so we have a couple other very recent corrosion projects that one of them locally in the area that we thought might be of interest to you. They're really kind of oddball, and you're going to kind of scratch your head and go, how can that be? But that's the way corrosion is. We thought it might be of interest to have you take a look at these as well. And we'll answer any questions you have to get in here.
Yeah, you'll see some of the same kind of tools and methods that Ray talked about. We're a bunch of here, I'm sure, get into the project, but I want to, like Ray said, share some of the things we've learned in the last few years and some other interesting corrosion projects. Talk about a bridge in Green Bay, Wisconsin called Vito Frigo. Theater here in Southern California, some stairs that experience some corrosion, and then also Ring Colorado, which is a bridge down in Southwest Florida, also has some interesting corrosion. So the first one, late 70s construction, Vito Frigo Bridge, Interstate 43 over the Fox River, major interstate for commerce, as well as connecting the two sides of the city on either side of the Fox River. In late September, a truck driver going over the bridge at about 4:30 in the morning, ended up calling 911. He was going about 70 miles an hour, and all of a sudden hit this dip in the road that wasn't there on the previous trips. Several other calls came in 911 later. You can see very clearly once the sun came up in the morning, they found that pier 22 had actually sunk about 2 feet from where it was the evening before. There's some other pictures where you can see the distortion. We immediately shut down the bridge and started an investigation.
There was no earthquake, I can tell you that.
That's right. So started an investigation, and so basically looking at investigation of the pier, one of the first things, this foundation issue, started looking at an excavation adjacent to the pier. The pier itself, and it's basically about 6 foot thick concrete supported by steel H piles below. And as we progressed the investigation and got down to the bottom of the pier cap, this is what we saw in terms of the H piles below. You can see pretty significant necking down, the flange edges right here. And then at the portion that it failed, we actually saw that basically the H pile kind of moved past each other, and basically it buckled. There's enough steel section loss that it could no longer support its load. And so what you see here is the upper section of the pile here actually moving past the lower portion here in the web of the H-checks and has basically rolled over. So the other thing is very interesting type of corrosion. You see, it almost looks like wood. You have these longitudinal striations and steel edge pile, and you see the section is substantially diminished, and to the point where in some local areas you can actually put your finger through the flame. So it's pretty startling to see. You can see again, just on the flange edges, this is actually kind of almost like a knife edge condition where basically you just lost so much material that it just really gone down to zero along the edge. And at some point, you had lost enough mineral corrosion section modulus such that it just could no longer support the intended loads. So as part of the investigation, we went through and looked at where did you start with, and then where did you end up? This using ultrasonic thickness measurements, and this flange actually started about ½ inch thick. You can see just based on these readings, after over 35 to 40 years, ended up with basically losing half of the vegetation. This was not an area that had failed, so this is also a concern. There are 40 piers along this bridge, and only one of them failed. What are the other 39 look like? So that's part of our charge. So in addition to doing thickness measurements at some of the areas that were suspect, we also went through and we looked at some of the soil properties. And Ray talked earlier about the concrete resistivity, very similar type of test, where you're doing soil resistivity here and looking at the potential for the soil to be a corrosive environment. And at the end of the day, the cause of the corrosion was actually a little bit unique. It was actually called microbial-induced corrosion, or MIC. And so what it is that you actually have, as the name implies, you actually have microbes, which are creating an environment where you essentially have conducive conditions to corrosion. In that case, some people like to say, bugs are essentially eating your steel, but that's ultimately, what it comes down to. And so then, in addition to that, we talk about these microcells and macrocells, so that's kind of on a micro level, basically happening very locally where the conditions are conducive. But then what that ends up doing is now you have two different environments, if you will, and that ultimately drives what's called a macrocell, or a larger condition where now you've got just differential conditions and all drives to the macrocell or galvanocell. So we also found that of the 40 piers that were on this bridge, we opened up about 13 of them, and of those 13, only about 5 or so had very severe corrosion conditions. And what we found, was kind of the only factor, is that this area had been filled with fly ash heavy material, just kind of given some of the industry in the area, and so that created a very conducive environment for these microbes. And so that's where you have the most aggressive corrosion. And so in other areas where they had clays, you didn't have the correct environments for this, so you also didn't have the rivers adjacent to this area, so the transfer of water through those clays, it was okay. So, they said, okay, that's a good snapshot of where we are today, 40 years of life, where we're going in the future, because we want to be some other 40 years out of the bridge. And so we ended up going in and putting a long-term basic monitoring system, and we talked about the half cell potentials, very similar technology that we borrowed from the pipeline industry. This is, given the nature of pipelines, this is something that they face a lot, so they had some good tools that we were able to borrow. So that's a half cell potential there at the top right. And then in addition to that, it tells you about the kind of potential of the environment. And then we also did what we call corrosion rate, where basically you're literally taking this piece of steel, moving it around and seeing how fast it's corroding, and using that as a kind of a benchmark to compare against your steel piles that are done. So at the end of the day, they spent $20 million very quickly, in 4 months, trying to fix the bridge. They basically had to establish a new foundation and then actually raise the bridge, the superstructure, to kind of get rid of the dip. And then we came in several months later and installed the long-term monitoring system and continued monitoring that. This is actually the first application of this on a bridge, so it's pretty interesting to be able to see this data and look at it.
The Green Bay Packers fans were very upset.
Yes. That was the most important thing.
That was most important.
Yeah, interrupted football traffic. Next project we're going to talk about is some stairwells here for a major movie theater here in Southern California, primarily used for emergency egress, but during the routine inspection, they saw some corrosion and investigate a little further and see what should cause it. So here you see some very nice looking planters with some loading vias, but unfortunately the drainage was really well thought through. In this case, you can see right there, this is the drainage coming out, the splinter box is coming down and just going over the surface of steel. That's the area where we have the initial concern. Once we remove the fireproofing, you actually see it's fairly corroded. And the other thing that is of large concern is that it's a little tough to see in this photo, but this is actually coming down at the end of the beam where you have bolts of connection. These bolts are what's called slip critical, so any amount of section losses is very concerning. The other thing we found is, depending on where you were, you can move over similar to reinforcement, and 6 inches over, you're in good shape. Once you're doing fireproofing, say a couple feet over from the area of the drain, you're similarly, the steel is in fine shape and you didn't have the section loss. So we started looking at the fireproofing, and what we found is they had continued with the fireproofing that they were using on the interior of the building, which you don't have the exposure to the elements. They continue using that fireproofing on the outside of the building, where now you have the elements. And so basically it was a non-cementitious fireproofing and actually worked like a sponge. And so you have this water coming out of planters, taking fireproofing and then staying there, and then creating a corrosive environment in this area. And so this was not what was specified in the project. We actually specified a cementitious product, and so supposed to be like this. So we go through and using an ultrasonic thickness gauge, basically with a survey to identify where are the areas of section loss, and in some areas is up as high as 20% section loss, but I'd say by and large it was generally in good condition. Went through in the areas that we identify section loss, strengthening with weld steel plates, and then ultimately came back with proper cementitious fireproofing, which they installed. Great, which we just saw yesterday. Next project is Ringling Causeway, bridge down Southwest Florida. It was built in open traffic in 2000, and then experienced some pretty significant problems with the intersect. But they had installed what are called external post tensioning. So these are not within the cross section of the concrete. So these are ducts that are exposed along the length, about 300 feet long, and these are routed along the length for corrosion protection. But as we'll see in the next slides, the corrosion protection ended up being what ended up killing these tendons. During routine maintenance on the bridge, inspector had found one of these external tendons laying on the bottom of the inside of the box there, and these things are actually supporting, or excuse me, tension essentially about 1 million pounds. So a significant amount of force, to the point where you blew out some of the concrete, and you can't see them here, but there are whip marks on the inside of the concrete where when this thing fails, thrashed around until all the tension was pretty violent. A couple months later, they're teared down. A couple months later, another maintenance walking saw another one. So DOT became very concerned at this point, and so we're inspection of all these internal tendons at the high points, which seem to be where this failure is occurring. So they found pretty severe corrosion. And then in addition, this is actually supposed to be entirely filled with grout. You can see just a significant void here. This is at the high points of this external tendon. So they took these, some of the failed tendons, and they wanted to look at some of the residual materials, the strain as well as the grout, and took it back to the laboratory. And the interesting thing is that it seemed to be kind of a localized phenomenon. You can see on the top side of the strand here, the strand to be in good condition, but the underside of the tendon, you can see there's a wire break right there. I see the strands are corroded. And so there's something going on kind of on a localized level. So utilize half cell potentials. Again, similar to what we use for reinforced concrete. We connected to the strand as well as to the grout. And looking at this cross section, talk about how the steel is corroded in some areas and appear to be in good condition in others. we identified essentially just looking at the cross section, there was just an area that appeared to be, soft grout or kind of raw material in this area right here. And so we found in the same range that we just found there's an increased potential as you get into the soft grout. So it just looks like an environment that's more conducive. But as you can see, kind of 80% or so strands in this area are fine and are not in a corrosive environment. And if you were to take them out of that tendon, they would look like the day you installed them. And so we ended up really focusing on the grout here, and what we found is that along the profile of the tendon, actually the properties of the material of the grout actually change. And so here at the low point, there's less moisture than at the high point. The concentration of sulfur is higher at the high point. Chlorides, like I said, generally bad for corrosion, also higher. And then the other interesting thing is that steel in a high pH environment is generally pretty happy. It's what's called passivated. You generally don't have corrosion, but in this case, very aggressive corrosion, but you still have the high pH environment, so that's a little bit of a head scratcher. But what we found is that essentially you had a segregation of material. Seen on concrete placements, after a little while, eventually bleed water comes up, as the material starts separating a little bit. It's a similar phenomenon in these prepackaged grouts that are used to put in additional tendons. And just as the material started to segregate, the cementitious material is more dense than the water, and so basically displacing water, and usually ends up with a lot of water and a lot of other materials that are kind of went along for the ride and ultimately settled here. And as it started downhill, left a void here once that water desiccated back into the throughout uphill, downhill from the high bank. So anyway, so as the water moved, it transported all these materials, and that's why you ended up with higher concentrations of sulfur and chlorides at the top area. We had that soft material at the top and the good material down below, and so we want to try to essentially recreate this environment. This essentially showed that could drive a corrosion cell. So what we did is we actually took some of the material from that test sample, reconstituted it into this little bin where we took the area of steel of the suspect area, the area of steel of the good grout, and basically had hard grout, soft grout, and basically just looked at the current between the two, and then ultimately, after letting it run for several weeks, also saw that yes, in fact, that we were able to drive corrosion by see the corrosion product forming here just by having the essentially two different grouts of one. So basically, this grout segregation on its own, no additional outside materials or chloride, seawater, whatever, was able to drive this corrosion process. Went through and did some product testing. We took this material and did sort of plug and find tube test, and where you can see this is essentially going uphill. And essentially, as this material starts to break down after it's placed, water starts going up, and we're able to essentially show that the material segregated, and you ended up with this substantial amount of bleed water on the top. This is after 3 hours. It was a little bit dark, but you can see there's inconsistencies in the material. And then a few months later, when it was opened up in autopsy, the material actually, interestingly, after several months, was even still soft. You could literally do just like putty and take it, which is obviously not what you want if you're going for something such as grout. Took a look and basically looked at there was inconsistencies along the bridge. Some areas had it, some areas did not. There were 120 tendons, only 13 of which were corroded, so we were trying to figure that out. Basically ended up looking at different batches out of the plant, and what we found was that depending on which batch, you got very different results. There's series tests, and the interesting thing there on the right is that those tests were performed same day, same weather, same temperature, same water, etc. But we got two different results depending on which batch you're actually looking at. And we also found that there's not a lot of quality control. When you look at such as the weight of the bags, and so the weight of the bags, how much water you have goes to the water cement ratio, which has an influence on bleed. And what we found is that one batch they had very good grouping around the nominal weight of the bag, which is 50 pounds, and then another batch, they were all over the place in terms of how much product was actually in the bag, which will ultimately affect their performance of the material. questions, whether it be for Ventura or for some of the more recent stuff.
I want to thank you guys for helping out, especially,
I was thinking someone else might ask a question, but I'll go ahead. I got a couple of things. One is and I know we talked a little bit about this on the phone when you guys were doing your study, but one of the construction specifications that we have for placing concrete on a starter wall is actually putting a couple of inches of concrete paste at the bottom of the wall. It seemed like on the phone when we, and I don't know if you remember that conversation, your initial response was that you weren't sure that would be a good idea.
Yeah.
Did you ever come to any further conclusions on that? Or?
Yeah. Here's my reason I had that conclusion, because I've seen that, I say done not specifically for the wall, but I've seen paste like that done, and it kind of laying out a mortar in order to make sure it's and sealed. But if it's done very quickly and done well, it could probably very well help. But I've seen a lot of cases where that dries out and it almost ends up being another void along there. So it depends on, because you're having to do it very quickly. You got to put that mud. It's kind of a mud mat.
Right.
Putting mud down and then pouring the concrete,
Right.
and you got a tall wall vibrating, get that all done. The other thing that we're seeing, in fluid-containing structures, they use water stops, and I would suggest that here, but necessarily. But the other thing that we're seeing in the industry is they have various types of water stop type systems that seal along the edge. There are tubes, and then they inject urethane out along the side, so they do not allow any ingress. And there's ones that there's strips that you can put down that expand and do that. Those have been fairly effective.
Yeah, we do use water stops, and we're in the process of updating our chapter on this area.
So, is the water stop not a center mold water stop, like one side of the wall on like a polyvinyl chloride water stop?
Well, yeah, it is that kind, and sometimes there's a couple different water stops.
Yeah.
Sometimes if we're concerned about water going into the wall from the channel, then we'll put a center bulb, like high tidal areas. But more often than not, what we're using is something that's going to be on the outside.
And that's the challenge of the flood control. I mean, you really got both, right? You really got the water from on the inside, but you also have the moisture on the backside. That was the problem at Marina Del Rey. You had the tidal fluctuations, the water going up and down right near a construction joint, but the water went through the joint, and on the backside, the soil, it lags behind the drop in tidal, and so then it goes slower, and then it can go back out across the other way. So you really have to have kind of two systems, or a system that precludes it from getting to the backside of the wall. I like the double, these wall panels. The older ones traditionally have only had, I like the idea of two, just because of the redundancy, two mats of reinforcing steel. Not that the other mat would necessarily be overly helpful, but it would help to some degree, I think, in terms of the integrity. But I think that joint's the critical area, so it really, I would have to see it in place. It could work. I've just seen too many cases where a mud mat gets dry, it doesn't get intermixed well, and you end up putting another void down here. So water stop that could be injected after you install it, that really fills that seam. That's really what I'm seeing people do in the industry.
One other question. This morning we went out to Arendelle and saw some problems out there. One of them was ASR, and we talked a little bit about how much that seems to be a predominant issue with our concrete structures where we have problems. And I was just thinking, wouldn't it be great if there was an admixture that would sort of minimize that, realizing that we still need to do testing of the aggregates and making sure that we keep that risk down to a minimum. But are you aware of anything like that?
Yeah, well, there are some that aren't, nothing's commercially available that I'm aware of, okay? So the one that people have used that, and if, I'm not sure I can describe all the chemistry myself, but is lithium, that they actually, a lithium-based product that they admix into the concrete. If it's admixed, it's shown to work pretty well. They've tried to do that as kind of a retro process where you go out and inject a lithium base. That hasn't worked that well, but as an admixture, lithium seems to have some promise. I'm not aware of any commercially available product though that does that.
Someone came up with one, they could make a lot of money.
They make a lot of money. I mean, you got, you know, we everywhere. It's not just California. I mean, we're using up our natural resources, and so the aggregate supplies we have are being drained, and you know, the good stuff is going. Now we got to use the bad stuff, and we're going to face that problem for generations and forever. So we gotta work on it.
Roughly how old was the Oxnard Restaurant when that wall collapsed?
Built in the early 70s. I think that was the date, so
That's about right.
40 years.
20 years.
Yeah, we started building channels with double mats right in the late 60s, early 70s, and that was a double mat channel design.
Yeah.
So the stuff out in Moore Park and City Valley, that's all, you know, pre 1970s.
Yeah, single mat. So the double mat didn't help you there.
No, not absolutely.
We got both mats,
Yeah,
and
it
then you
did.
don't have much moment arm left on that other side. So.
Gotcha.
Is there any way to intervene the corrosion process at an early stage of the accelerated corrosion?
So to interrupt the process, yeah.
To intervene, interrupt.
Yeah, so, you know, and that, there's a whole, and, you know, some of it's worked, some of it hasn't worked, some of it works sometimes and other times. So epoxy coated reinforcement, of course, has been, people are looking at alternative alloy, you know, types of steels that are more resistant to corrosion. It doesn't stop corrosion, but it slowed, the corrosion mechanism slowed up. One of the things I've done in terms of repair design and whatever that I like is a corrosion inhibitors in concrete, admixed in concrete. There are a number of corrosion inhibitors that are admixtures that work fairly well. Calcium nitride is the most popular one, so that is something, and what that really, you can think of it as kind of raising that chloride corrosion threshold. Instead of it being like 300 parts per million, it's like increasing it to a couple thousand parts per million. So effectively, that's making it a lot higher threshold before corrosion can actually occur. You know, epoxy coated bars, they've had some problems because of the epoxy on the coating, and if it ever gets damaged in construction, then you can get underfilm corrosion, and there have been some bad corrosion cases. So you actively accelerated the corrosion in some cases. So there's nothing, you know, I don't have, I like corrosion, I like, you know, black steel, regular reinforcing steel, high quality concrete, low water cementitious ratio, and I will make some use of corrosion inhibitors in concrete.
And we've taken the same approach.
Yeah.
That not to do the epoxy coated,
Yeah.
using the water stop as an additional
Yeah.
protection.
And you might, the water stop, and I'm not sure which ones, but you know, some of these ones that I've seen where you're really, it's almost a post that you put it down, it's almost, and some of them are tubes, some of them are strips, and it's a post injection where it's like putting a seal right down across the whole thing, and it prevents water penetration.
We haven't done those.
Yeah.
The ones that we've done basically across the joint.
Yeah, the center, like a center bowl. Yeah,
or-
yeah. And, you know, depending on what you think your main water source is, then it can be effective.
One more quick question to Michael, right? How did they repair the bridge?
The first bridge or the second bridge?
The first one.
They, at that pier, they actually ended up building drill shafts, you know, on either side of the existing steel foundations. And then for the first, I believe, 30 feet, they actually used a large diameter PVC, you know, liner to essentially get through that fly ash area that I had mentioned, just to preclude future corrosion of the concrete drill shaft. And then they tied that to the pier cap, you know, through some post tensioning, as well as some bars drilled into the existing pier cap. So they had some buttress type structures at the base, and then that didn't elevate the pier, and so they still had the top with the dip. And so what they ended up doing was cutting the superstructure free, and then jacking it up, and then eventually filling in that 2-foot gap to get rid of the dip. And so basically it came on top of the hammerhead at the top, and put 2 feet of concrete or something below the supports.
Sure.
Yeah, well, the interesting thing, I talked to Mike and another gentleman in our office who's really quite an expert in corrosion, and he as well, and there's actually a connection in my mind between that Leo Frigo bridge and then the one in Florida, the Ringling Bridge. Both of them, I mean, they're, I still in my day scratch my head, believe, kind of microorganism, and really what was happening is the microorganisms that are called sulfate reducing bacteria, and they produce an acid, and it's really the acid that created those the gaps and ate into the steel. It was the acid that comes from the microbes. But what led to those sulfate reducing bacteria was the fly ash. So all this bottom ash that came from this coal-fired plant that they've been dumping all this stuff in for the years, that was rich in sulfates. What you saw on that Ringling when we did the chemical analysis, that separated the wet grout, the soft grout from the good grout, it had much higher sulfates in it as well. And that's the interesting thing, is sulfates aren't known to be corrosive because they still have maintained a high pH. So we're really getting corrosion in a very high pH environment, and both of them are related somehow in my mind, or something related to the sulfate content. And so I think we've got a lot to work on. It's a very, the Leo Frigo, I think people were concerned was, how many thousands of steel piled bridges do we have in the United States, and could they all be at risk from that? And my answer is no, I don't think so, because the rest of the piers were all in clay. They may be wet, but as long as it's wet, you don't get a lot of oxygen, or you don't have a lot of other things going on, then, perfectly fine. It was that layer of, I don't know, 10 or 12 feet of stuff, this ash that they had dumped there, which was really the area that presented a problem.
So just perfect environment for these little microbes that doesn't happen very often.
That's
Do you typically see any utilization of fiberglass rebar as opposed to the epoxy coated or?
Certainly the FRPs, fiber reinforced plastics, all sorts are being utilized. Where I've really seen them commercially, it has nothing to do with corrosion. It has to be in medical centers imaging centers where they want a non-magnetic type of reinforcing steel. To see that all the time in hospitals now. It's really been a hit, a couple of prototype structures, trial structures where they've used FRP, not in mass that are you seeing it. You don't see a bridge here, a bridge there, but it's being thought of, being looked at, but just not catching on.
How deep can ASR affect the internal pH of concrete?
Can ASR affect the internal pH of concrete?
How deep can it?
Oh, how deep can it go? Well, it can go throughout. But what happens, it depends on how much reactive stuff is in there in terms of these the silica and the aggregates. What we've seen is typically, we've seen some concrete that can go through thickness, but it's such the aggregates were so unsound, and the cement had so much alkali in it that it can never burn itself out, so it can go deeper. Typically what we see in others is that it tends to be localized only where moisture has direct contact, and it tends to not then penetrate too deep. So you have a kind of a zone of bad stuff, but then internally beyond that it's kind of well protected beyond it. So it just kind of depends on how bad the aggregates are and how much moisture is feeding it.
So how thick the numbers do.
Yeah.
A small slab versus deep grading.
All right, well, it's 1 o'clock. We'll stick around.
Yeah.
Talk to Rick.
Yeah.
I'd like to thank you guys.
This is like from
Did you play against the Charlotte Show or was it in Austin? Were you in Austin?